Okay, so last time we were looking at the Bode diagram and we were deriving the L function.
Hello?
Sorry, was there a comment? Okay, so we were looking at the log modulus, so that's the L, so we had derived that L function. So here I'm just showing the notes. So this is what we did last time, right? So generally speaking, we are plotting L and theta. And the reason we are doing that is because we had established this criterion for ourselves last time. So just to sketch that out. So we have the criterion that we want to evaluate. So criterion for stability encirclement of -1, 0 on the G plane. So we want to know whether we encircle the -1, 0 point on our G plane. And that's and to do that, we said we have to traverse the entire right-hand plane. And then we found there were three that we could do that in three parts. We could use S equals I omega. Then we can use S goes to infinity, traveling on the positive real part side, and then S equals minus I omega. So eventually, we found that at infinity, that we would never encircle -1, 0, that G would go to 0, because if G has more denominators, if the denominator order, excuse me, is high, then G goes to 0 at infinity. So we don't, let's draw it a bit. So this is what we said. Yeah, so we were encircling the entire right-hand plane. We said this part is fine. So this S equals I omega, that's something that that may give us some information about G. Then we also had this this part to encircle the entire right-hand plane. So this line has a radius of infinity, and then we come back home here. And so we had said S equals I omega. We know we can get G along this line just by using our frequency domain function. And then here, the magnitude of S is going to infinity. And if that's the case, G goes to 0. So that's not going to encircle -1, 0. And then this is S equals minus I infinity. So that's just going to give us it's going to give us the complex conjugate. G is just going to be the complex conjugate of what we have here. So there's no new information from down here. So we only have to look at S equals I omega. And now the challenge is that this is in the S plane, and it can be a little difficult to figure out what that means in terms of G. So we know that as S travels around, G is going to do something else. So G is in its own way. So the question is, how do we visualize this? It seems a little bit complicated to visualize what's happening in G. So even though we have this nice relationship between S and G on S equals I omega, right? So even though we have the basic theorem, and so according to the basic theorem, we have G of I omega is equal to the magnitude ratio and the angle of G of I omega. That's equal to the phase shift. So we have this relationship. This tells us that if we just pulse in some sine waves and measure the magnitude ratio and we measure the phase angle, then that will give us G of I omega. So we know we can get this at least. But still, it's a question how we'll plot that out. How will we actually use that to develop our controllers? So one is, of course, we can just try and plot it here on the complex plane. But the alternate suggestion is that we do it instead using this definition. So yes, we can always plot G like this. So when we've got G of I omega and the angle of G of I omega, we can just go ahead and plot it on the complex plane. But it's a bit harder to imagine how to move it around. How, for example, when you increase the proportional controller, what happens to this graph? It's not so clear here. Whereas in the Bode diagram, we have an alternative. So in the Bode diagram, this is more like plotting polar coordinates using two pairs of axes. So one is we plot the magnitude of G, but we do that with a log of that magnitude. And for the angle, we do just go ahead and plot the angle. So that one we don't change, but for the magnitude, we take the log of the magnitude. And we talked about how to work out this L function last time. So we said, let's say we have this original function. So for a process given by, so G of S equals 1 over 1 plus tau S. So if we have this transfer function, then when we apply I omega for S, then it looks like this. And if we multiply by the complex conjugate in the numerator and denominator, then we get rid of the imaginary part in the denominator, leaving us with this. And if you think about this line, right, you've got a real part in the denominator, a real number in the denominator, and then a fixed number here. As omega increases, this will overall decrease. And here, as omega increases, this will also overall decrease. And as omega increases, this part will increase faster than this part, right? They have the same denominator, but there's no omega here. So in the real part, the omega, the increase in omega won't improve this part, whereas the increase in omega will cause this to increase. So that's part of the things we can think about there. In both cases, though, the denominator does mean that overall they'll both decrease. So then what we said was, well, if we want L, then we need the magnitude of G of I omega. And so the real part squared plus the imaginary part squared, all square rooted, it looks like this. And so we got that function. And what we actually need is L. So it's 20 log 10 of the magnitude of G of I omega. And if you take 20 log 10 of this, you can recognize that you would rather write this as 1 plus tau squared omega squared all raised to the power minus 1 over 2, because we know we can take that power out in front here, leaving us with minus 10 of this. And then we said for small values of omega, the second term vanished, leaving us with log 1, which is 0. And when omega is large, then the 1 plus part, that is small in comparison, leaving us with tau squared omega squared. And we could, of course, rewrite that by taking the 2 in front here. So it's minus 20 log 10 tau omega. And of course, omega is the thing that is varying, right? Tau is not changing. Tau is a process variable. Tau comes from our original process. We have no easy way to change that, at least from the perspective of control. So we assume that's not changing. But omega is changing because we are doing a series of experiments. So in all this, don't forget that by the end of the day, we have some process. So our process is somewhere, and we might not know what it is. There's an input and there's an output, and we can apply a sine wave at the inlet or the input for the input. And we can apply another sine wave, which maybe it has a longer period or a lower frequency or we could apply another high frequency one and make it do this instead. So we are able to change omega. So we are changing omega, and we are observing how the magnitude changes. And as we said many times now, we get that magnitude by observing the y, and we look at the amplitude of y here, and we look at the amplitude of u here. And so the magnitude ratio is equal to y over bar the height of y, the maximum height, over u over bar the maximum height of u. So we can get the magnitude ratio, which, as we know, is nothing but the magnitude of g of I omega. And so we can get this as a number. So we can get MR as a number that gives us the magnitude, and then we can just get L, right? So I'm saying all that to emphasize that from the simple experiment, we can actually construct L. And in fact, I've set your exam, and in the exam, you do have to use that. You have to be able to take data like this and translate it into magnitude ratios and L and all of that. Okay, so are we all on the same page about that? Any questions or comments there? Okay, so that's how we can get L. And it just so happens in this case, we are given the equation. And so for that equation, we can say those are, so at low values, L looks like this. At larger values, L looks like this. And here we've said tau is a constant. So this part, 20 log 10 tau, that's constant. But we know omega is changing. And in fact, our x-axis is log 10 omega. So this is like x. And so we have a constant gradient here, minus 20. So we said, if we were to graph that, we could just go. If we were to graph that for L, that we would have a 0. We would have a 0 for low values of omega. We said that was one asymptote. And that when we got to a certain point, and omega was large enough that we could ignore the one, then this equation applies. And here we can see 20 log 10 omega. So the slope here is minus 20. So in this case, we will eventually end up on this line, right? So that's our L function. And the question is, when do we get this crossover? So if you look at this line, you can just extend it backwards. You can ask, when does L equal 0? And so L equals 0 means that these two terms are equal. And these two terms become equal when omega equals 1 over tau. So this is the point 1 over tau here. I'll just call it T. Okay, any questions or comments on that? Okay, so that's what we get for the L part. So this is L plotted against log of omega. Okay, now the other thing we need to do is also get the angle. And if we think about the angle here, you can see that the real part is not changing with omega, whereas the imaginary part is growing with omega. So we could say here, and it's negative, right? It becomes negative. So we can say that if we were to imagine how our G function looks, it seems like the real part, it's moving around here. The real part, it's 1. So let's say there's a 1 here. But also that real part, it is decreasing as well. So as omega increases, that one is moving in like this. Then as omega increases, we do have the imaginary part. Where is here the imaginary part? This is increasing with omega. It is also decreasing on balance. But if you perhaps take the ratio here, you could say that the imaginary part is outpacing the real part. So the imaginary part is still increasing relative to the real part. So if you were to take the ratio of those two, the imaginary part over the real part, that is on balance linear in omega. So relative to the real part, the imaginary part is going up to infinity. And so what that tells us is that you can start on 0 for the, 1 second, just right. So you can imagine then that for omega equals 0, we only have a real part. So the angle is 0, right? If you look at this, initially you are sitting somewhere here. So if I were to plot G on the imaginary plane, if we look at the equation here, the imaginary part is 0 when omega is 0. So imaginary part is 0 and the real part is some constant. That means we are sitting somewhere here. And so this angle is 0, right? This is an angle of 0. So if we were to plot theta, we would start on 0. And then as omega increases, this point is moving upwards. So the imaginary part is increasing and the real part is, well, both are decreasing, but the imaginary part is going faster, is increasing faster. So it's becoming more and more a point that's moving up here. So it's becoming a pure imaginary number. So if we can imagine a point here, we can see then the angle is 90 degrees. So that's a 90. So what will happen here is this one will come down to a 90. So that's the angle part of the Bode diagram for this particular function. Okay, any questions or comments there? And the location of this is, of course, where omega is 1 over tau, just like we had for the log modulus. Okay, so that's what we can get for 1 over 1 plus tau s. And then we can do a similar thing for just 1 plus tau s. If we go, I guess it's here. No. Yeah. So, so this was a so-called first order lag. So this was a first order lag. So that's what we've talked about here. Right. And in fact, yeah, this is a bit more clearly explained here. The angle, you can also, instead of just imagining it, the imaginary part and the real part, you can say that the angle is identically equal to the arctan of, this should be the imaginary part over the real part, not real over imaginary. Please make that note there. So imaginary over real. Then you get a function that looks like this. And clearly at 0, arctan of that is 0. At infinity, arctan is minus 90. So this is minus infinity, so minus 90. So those are the two graphs that we got here. And we said 0 and minus 90. In this case, I'm doing it in terms of pi. So 90 degrees is, of course, pi over 2. So this is minus pi over 2 or minus 90 degrees. So that's how your angle changes there. Okay, you could also plot the real and imaginary parts like this, or you could plot the magnitude ratio as well. But anyway, let's just stick to these two for now. Okay, so that's the first order lag. Then a first order lead will look like this instead. So 1 plus tau s. And so G equals I omega tau. So in this case, it's not in the denominator, so there's no need to multiply by complex conjugates. It's just straightforward. We've got the real part and we've got the imaginary part here. And so the magnitude of this, of course, is the square root of the sum of the squares. So it will look like this. And so that's the magnitude done. And then for the angle, again, you'll say the arctan of the imaginary part over the real part. So that's there. And maybe just thinking about it in terms of on the complex plane, let's just graph that on the complex plane. So the G part, it's 1 plus I omega. So the real part is always going to be a 1 here, right? So even when omega is 0, your real part is a 1. When omega goes to infinity, there's still a plus 1 here. So the real part is fixed at a 1. So that means we are only ever traveling along this line for this function. And so we can say then the magnitude is increasing as we travel up here. The angle is also increasing, right? Initially, your angle was 0 here, then the angle increased to this value, and then it increased to that value, and so on. And we can imagine when this point moves infinitely far away, we can imagine the situation looks much more like this, that there is a little 1 here, but we've moved so far up here that in essence, we are sitting on the imaginary axis. And so the angle has gone from 0 to plus 90 degrees now. And so there's a nice little symmetry that comes up here. You get your angle going from 0 to plus 90. Remember, in the previous case, the angle went from 0 to minus 90. And also, if we look at the log modulus, and you can do the same story for the log modulus here. So let's just do that. So for the lead, we can say L equals 20 log 10 of the magnitude of G. And the magnitude of G here is the square root of 1 plus tau squared omega squared. So that's L. And then we can rewrite this as, so that square root is, of course, raised to the power 1/2. So we can rewrite this as 10 times 10 times log 10 of this stuff. 10 times log 10 of that. And then again, we can say for small omega, we have the equation looking like this. It's going to be L is approximately equal to, and yeah, for small omega, then this part will vanish. And so this equals 0. So again, we are getting 0. We are getting 0 for small values of omega. And we can say for large omega, then we have for large omega, this is approximately so for large omega, tau squared omega squared is much more than the 1. So it looks like this, and this is nothing but the square root of tau omega, right? The squares and the square root give us tau omega. And so again, we could split the two variables there. So we can say this one, right? Because the property of log is the log of the product of two things is equal to the sum of the logs of each of the individual things, right? So again, this tau is a constant, and then we've got a gradient of 20, and our x-axis is log 10 of omega. So we just get a gradient of plus 20 now. So when we plot this, we get a 0 for low values. There's a crossover again at 1 over tau, and there's a slope of plus 20 decibels per decade, right? So we say decibels because that's the log scale, and then per decade, again, log scale, factors of 10 here. So we've got 0 going to a plus 20, and we've got the angle going from 0 to plus 90. And that's the first order lead case. And then in the so-called first order lag case, we have, instead of going the upper asymptote, instead of going to a plus 20, in this case, we have a minus 20 as the slope. And for the angle, instead of going from 0 to plus 90, we go from 0 to minus 90. So there's a kind of nice symmetry between the Bode diagrams when you have the first order lead and the first order lag. Yeah. Now, a couple other things we could say here is, well, let's pose the question first. We could say this is all well and good for those two nice functions, but what if we have something more extreme than that? What if we have something like this? So we've got s minus 0 here and s minus 0 there, s minus, and maybe there are m zeros. And let's see, I need a ratio here now. Yeah. And now I have the poles in the denominator. So we'll have n poles instead. N poles, right? So that's generally what we have. We described earlier that you could pose whatever the form of function was, you could eventually show you can reduce it to this form. And the nice thing about this is that the magnitude here, g of I omega, can be composed as the product of each of these. So you could simply take the magnitude of each of these terms and multiply them together. And so the way I would write this is to say pi, capital pi, s minus I, or rather I omega minus, and I guess we have to call it k. This will be, let's say this is for the jth one. Yeah. And this is raised to the power n I. Oops. Raised to the power n I. Okay, so what we're saying here is that we can recognize that this g function is obtained by multiplying together all these all these s minus z and s minus p. So when we apply g equals I omega, we can use this multiplier operator, right? It's the same as our sigma for summing things up. So sigma, right? That's if you are adding things. In this case, we are multiplying things. So we are saying we've got this kind of form S minus something, and we are applying I omega. So it's I omega, so of the minus something, whether it's Z or P. And then we are introducing this here because all these ones, the zeros will have ones. And for down here, we'll need a minus one. And what about the case where maybe one of them is squared or something like that? Then we have enough flexibility here. We could just use a 2 for that case, right? So that's if you like, the generalized form for G. In fact, we don't need the magnitude as yet. So that's the general form of G. And then we can also say, well, the magnitude then can be obtained just by multiplying all these things together as well. So the magnitude of G of I omega is nothing but the magnitude of each of these pieces raised to the ni. And what we actually want is 20 log 10 of this. So if we want L, L is 20 log 10 of this thing. So 20 log 10 of all this is our L. And then you can say, well, then I might as well take this Ni out in front if it's the log, or, well, we can't do it in the general form. But what this tells us then is that L can be constructed simply as, let's write it as a series of things. So we can say here, this is equal to 20 times, and then we can say N1. So whatever that exponent is, we can take that N1 in front. So N1 times log 10 of I omega minus K1. So that's taking the first term. And then we can add the second term. And this one will have a K2 and an N2 plus. And we can keep going until, I guess, the last one. Yeah, the choice of N wasn't good here. I shouldn't have used an N because, well, let me just call this N, let's not P, like it's just a Q. So there are Q poles over here. So we can stick to the N's here. Yeah, so there are N of these. And so we add up all the way. And so this tells us that our log modulus plot can be obtained simply by looking up the crossover frequency and taking our N times 20. So that gives us a way to plot these log things. So in fact, let's do a simple one here. So let's say G of S equals, and let's take this as 10 times S plus 1 divided by, and let's make this S divided by 10 plus 1, and let's say squared. So let's see how to draw that. So the first thing I can say is that, well, I happen to know that this piece here is going to contribute a line that gives me a straight piece. So let's sketch it here. Let's try and get these on the same page. Right, so this is the function we are trying to draw. So let's draw this piece first, 10s plus 1. And we are doing the L versus log omega. Okay, so for this part, the crossover frequency is going to be 1/10, right? So that's going to be, let's say it's here, 1/10, so 0.1. And of course, that's log of 0.1. So this is going to be a -1. And this is in the numerator. So n is a +1. So it's going to give us the first order lead. So this piece looks like this. It's going to be 0 between here. It's going to be 0 from 0 up to the crossover point. And after that, it's going to have a slope of +20. So that first term in the numerator will have this. Yeah, it will look like this. So let's just label this as a slope equals +20. And then for the next piece, we have S divided by 10 here. So the crossover frequency here is going to be at 10, right? Omega equals 10. So if omega is 10, then this is a 1. So the other one to draw is here, and it starts out at a 1, or rather the crossover is at a 1. Let's take another color. So the crossover is at a 1. And now this is a lag, right? So this one is going to start at 0, and at the crossover, it goes down at a slope of -20. But there are actually 2 of them. So in other words, you could draw this, we know we could rewrite this as S/10 + 1 times S/10 + 1, right? Because it's squared. So we can say then that the sum of those 2 is going to give me a slope not of 20, but of 40. So -40 will be the slope I'll get then. So if I were to plot this, I'll start out at 0. So we start at 0. And in fact, our crossover here is at 1, not at -1. So we keep going until we reach here. And then our slope now is sharper. So this is a slope of -40. So if we were to write that here, slope equals -40, right? So those are the 2 terms, right? The blue for the numerator and green for the denominator. And now let's imagine, so we want the overall, we don't want the individual parts here. We want the overall G, or the L for the overall G. So let's imagine plotting this, or let's imagine adding these pieces together. So when we start from 0 here, we can see it's 0 plus 0. So that's just going to be 0. Then from this point on, the green part is still 0. So when we add the blue parts, we'll just be following the blue line for the sum. So it will do something like that. And then we get to the green part, and the green part is dropping faster. So it has a slope of -40, whereas this is +20. So on balance, the slope is going to be -20. So we'll get a line that looks like this here. So that's the overall G function, or the L for the overall G function, this black line. If we add together those 2 parts, then that's what we get. And you see, that gives us a nice, easy, quick way of drawing our L function. Right? Because of everything we've said here, we can just view the numerator and denominator. We can see we just need to multiply the n value by 20. And then if it's in the numerator, it's a plus 20. If it's in the denominator, it's a minus 20. In this case, it was minus 2 times 20, so minus 40. So the question in the chat, Annika, is the slope not 10? So do you mean of the black line? Right. Okay, so let's maybe let's take some points here, right? So let's say the value here is, let's say this point here had a value of, I don't know, 200. So we have 200 here, and let's take a point here. And similarly, we take a point, I guess that's here, and then we take another point here. And let's just call this a unit step of 1, right? And it's about right, because that's -1 to 0 and 0 to 1. So let's say this is a distance of 1. So we've got, what did we say, 200 or something. So if this L value is 200, then the value here is going to be 220, right? So it's 1 times 20. The slope is 20, and the distance is 1. So that's an increase of 20 there. Down here, your value is 0, and your slope is minus 40. So this value is going to be minus 40. So if we add these two numbers together, it's 220 minus 40 equals 180. So our new value is 180. And 180, you can see 180 is going to be somewhere here. 180. Right? If 200 is here, that's 220. Then you can see 180 is there. So this slope, you can see on balance, because you are subtracting 40 and 20, it's going to work out that way. So you could generalize this form here, and effectively you'll find that you are subtracting the two slopes. So your plus 20 minus 40 gives you on balance minus 20. So this slope is minus 20. So I'm not sure if that helped, playing around with those numbers and seeing it agrees with minus 20. So we found it landed here. Did that cover it, Annika? Yeah. So yeah, you add the slopes and then you get that line. And so that means, as complicated as our function gets, no matter how big this is, all we need to do is look up the crossover frequency, and then we can say it's 0 until the crossover frequency, and then depending on the power there, and we just, for denominators, call it a negative, then we just multiply a 20 by the power, and that gives us a slope. And that line will continue that way indefinitely. So that's how we get each contribution. And then we just add together all the contributions, and that gives us L. In other words, we are able to very rapidly graph even a complicated function like this. We can graph it very quickly. So that's the beauty of the Bode diagram. It exploits the relationships with the logs to make it easy to do graphical addition. Okay. And then let's think about also the angles. So let's do the angular one. So we'll use another pair of axes. And so for the term in the numerator, that's a first order lead, right? So it's going to start from 0, and then let's mark off our points here. So we know that the important points for us are -1 and +1. Why does that say 0? That, I guess, was the value. But this is a 1 here. I don't remember why that's this. So that's 1. I guess we had the 1 there. So so for the numerator, it's a first order lead. And so this is going to go from 0 to +90 degrees. So it's going to do this. It will go, and this one is 4, 1/10. So yeah, that's the crossover frequency. The -1 is the crossover frequency. So this graph is going to go, it's going to be 0 initially, and then it's going to go to +90 degrees. Let's just put 90 degrees here, and let's curve it a bit. So there's 90 degrees, and we can just emphasize that it takes a bit of time to get there. Okay, so that's the numerator. And then for the denominator, the crossover is at 10, so it's here. And we are going from 0 to -90. If it wasn't squared, we'd be going to -90. But because it's squared, we can imagine there are 2 terms, each contributing -90. So this one will go to -180. So it's going to be 0 up to this point. It's going to be 0. And then it's going to go to -90. So if that's, sorry, -180. So if this is +90, then 180 is somewhere around here. So let's, oops. Zero to here. And then that's -90, and then another -90 is about here. And then we just connect them. So that's the denominator. And then we add them together, so we can see up to this point, we will have just, up to this point, we'll have just 0. Let's use this color. So we'll just have a 0 here. I'm offsetting it a bit so that you can see. So it goes here. Then from this point on, the green part is still 0. So we'll just be close to the blue part. So we continue on the blue line. So we get to there. And then we've got a +90 degrees plus a -180 degrees. So on balance, it becomes a -180 degrees. So we end up here. Okay, and then we can do the curved line connection. So the sum eventually looks like this. So that's the angular part. Okay. Any questions or comments on that? And the reason that we are looking at this is, so the next part of this is, what are the critical values on this? And remember, the reason we are doing all of this is because we know that there is this point -10, which is the critical value for us. And we would like to know if our function encircles this point. So -10. And so if you imagine moving along these lines, right, you can see the magnitude of G is 1, then the magnitude of G increases. And while the magnitude of G is increasing here, the angle has shifted from 0 to plus 90. So we said the L is 0, means the magnitude was 1, and then we were on 0, the angle was 0. So that means we were here, and well, let's put this. So we started here, right? So this long section, this section here and this section here, right? We read an L value of 0 to mean the magnitude of G is a 1, right? So we are trying to plot here the real and imaginary parts of G. So when L equals 0, G equals 1. We know that from the definition of L. And we've got the angle here is equal to 0 as well. So the angle is 0. Now we can see, and I'll get rid of that. Now we can see when the magnitude increases. So if you imagine the circle, that there's a kind of hidden circle here. Now the circle on which G is sitting is getting bigger. The circle is getting bigger, but the angle is only increasing to 90 degrees. So it looks like G is moving towards that circle, but it's getting closer to 90 degrees. So it's doing something like that. And then after that, the magnitude of G starts decreasing. So now we are getting smaller, but the angle goes down to minus 90 degrees. So minus 90 degrees, minus 90 degrees, and it goes through these values. So in other words, it goes backwards. So the angle, it got to plus 90, now it starts to go backwards. So we start to shrink in here. So G, remember G is going down on balance now. Now we are looking here. So G is starting to go down. And so the magnitude, so G is being pulled in towards the origin, and the angle is decreasing. So it was at plus 90, now it's going towards minus 90. So it's starting to do this. And so it might do something like that, for example. So by having this Bode diagram, we can guess our way around this plane like this. We can imagine in the different sections what's happening, and we can observe from this whether we will encircle minus 1, 0. And it looks like from this, it looks like we will not encircle minus 1, 0. So in other words, if you imagine this line going further and further, this is only getting more and more negative. So the magnitude it's getting smaller and smaller. So the critical point would be somewhere here, right? When the magnitude is a 1, right? So all these values, this was the danger area for us. This is where L is more than 1. So it could possibly go past here if L is more than 1. Sorry, if the magnitude ratio is more than 1. But while we were in this region, we never got to a minus 180 or a plus 180. See, the angle here is 180 degrees. And we never got to 180 degrees. We only ever stayed between plus 90 and minus 90. So we were always tooling around over here. So we could never encircle minus 1, 0. And that means this is stable. So the concept here is that it's easy to draw Bode diagrams almost by inspection, right? And I did it long and laborious, and but if you just inspect this thing, you can see, okay, crossover frequency 1/10, 0, and then shove in a plus 20 here, and then crossover is 10, and so you can just by inspection quickly draw a Bode diagram, and then you look at the different pieces and you try and guess on your imaginary plane, how is that looking? And then you can tell, whether you are going to encircle that. So even though this is a fairly complicated function, it's not necessary to go and do all the work of converting complex conjugates and doing all that. We can quickly draw a Bode diagram, and we can quickly guesstimate whether or not we are encircling -1, 0. So plotting Bode diagrams, you should view that as an easy thing to do. And like I said, we've got all those examples in the tutorial. So work through all those case studies, please, and see that you are able to draw a Bode diagram quickly. Obviously, it's on the exam and the test and all of that. But even without that, yeah, you are able to very quickly tell whether a process is going to be stable. Imagine just from this function, you can quickly figure out whether or not it's going to be stable. So that's a big step forward for us. That's the beauty of the Bode diagram. Any questions or comments there? And then just to make it crazy easy, I've also got this, I wrote this Jupyter notebook for doing all our frequency domain dynamics. So you'll find it with this name 05 controller design. And if you open this, you can see here, this, this code will take any G function and produce the Bode diagram and a couple other diagrams that we'll meet later. So you'll find some functions here converting polar to Euclidean, and there's GC open loop and closed loop and all of that. So if you read through this code, you'll see it does what we expect it to do in terms of producing a Bode diagram. So this block here, right? The first block, obviously, just to load the libraries. This block is just to establish the functions that we use. And then in this block, we define our functions. So if we wanted to see the Bode diagram for this thing, for instance, let's just run all this. So just shift, enter, shift, enter, 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 enter. So here's the Bode diagram for this case. So the crossover frequency at 1/2 and 1/3. Now, those values are very close together. In fact, let's change this a bit. Let's make this, yeah, let's make this 10. And let's make this S/10. I don't know why I wanted to 50,000. Just say 5. And you can sort of see two different slopes here. So remember here, we've got the first crossover, which is the first one. I guess it's this one, right? The first crossover is at a value of 1/10. So log omega is -1 here. So at -1, you are going to get a slope of 20 decibels per decade. So that's what we have here. Here's -1, I mean 1/10. So you've got your -20 decibels per decade here. And then if you go here, yeah, then the next term that occurs at 10, right? Crossover is at 1/tau. Tau here is 1/10, so the crossover is at 10. So at 10, we get an additional -120. And so you get an additional -120, so the slope sharpens, and this is now a slope of 40. And you can just quickly check that. Yeah, if you look here, there's a factor of 10, and this looks to be about a 40. This, remember here, 0 to 40 is here, so it's about this thick. And so if you look here, yeah, it's about a 40, whereas here, right, 20 is about 1 unit width, so that's a distance of about 20. Okay, and maybe we can play around with it a bit more. Let's do this one. Let's put the square up here. So we expect this one to go up with a gradient of plus 40. And then when it reaches here, we'll get a minus 20 added to that. So let's run it. So yeah, it starts out with a slope of plus 40. So it's going up at a gradient of 40. Then the denominator kicks in near its crossover frequency, and it contributes a minus 20. So that minus 20 is not enough to overcome the plus 40. So we end up with the slope of plus 20 over here. And you could change this also. So if you, let's say, cube this, then it should go down unbalanced. And yeah, now we've got a slope of minus 20 there. Okay. The angle is also plotted here. A bit more weird stuff goes on here because I've glossed over the fact that the curvy parts persist a bit longer than the way I've drawn it. So when all the curvy parts interact with each other, it's a little bit harder to see where the function ends up. But in the asymptote, at least we can see where it is. Okay, so that's your Bode plot. You'll see a couple other things here as well. Number one, the Nyquist plot. Yeah, so the Nyquist plot is nothing but g of I omega, just the real part and imaginary part. So it's just the complex plane. So you'll hear this term Nyquist plot. So that just directly tells us about that. And in fact, it's hard to tell. You know, this is the most direct way to check for that minus 1, 0. But it's a bit harder to see with when the values are very large. So let's do a zoomed in version of this. So Nyquist, let's call it zoomed in. So we'll plot the same stuff. We'll need a new figure number to update the other figures. And let's zoom in terms of, so yeah, I never remember offhand. So math, verb, access limits. Okay, come get to the point. Okay, exclam like that. All right. So here we can say t exclam. So the x limits, let's say minus 2 and 1. Let's try y limits. Let's say minus 3 and 3. Okay. Okay, so yeah, this Nyquist zoomed in. It is zoomed in, but we don't have any evaluation. So this is the critical point, right? You can see imaginary part is 0, the real part is minus 1, but we haven't run far enough. So let's increase the frequency range. Where is my frequency? Yes, it's here. So let's make this even 30. Okay, so now we can see you have values reaching in here. So it ends up crossing only down here. So it looks like the way this thing works, it starts out here, it loops around. And the reason I zoomed in is here on the scale, we are on the scale 20,000 and 5,000. It's too big for us to tell whether or not it's encircling minus 1, 0. But when we zoom in, we can see we are not encircling minus 1, 0. So this process is stable. Okay, so yeah, play around with this. Of course, try all the examples, do it using the Bode diagrams, see that you're getting similar results here. It might be a bit wonky because of the curvy parts, but still it should be, you should get the right results there. You can see for the Nichols chart, we should also do that. I just want to correct this one quickly. You won't need this just yet. Nichols. So I think for my X limits, I want to go from 0 and minus 180. The Y limits from 0 to minus 12. Okay, so that's better. Yeah. All right. Anyway, so that's you can use the simulator to try out the different equations. Okay. Any questions or comments there? Okay, so there's a question. So Annika, what does it mean if we don't enclose minus 1, 0 on the Bode diagram? And in fact, it's worth us just going through that whole line of logic again, right? So let's do that before we go any further. So number one, remember that we are concerned about poles in the right-hand plane. So in other words, we know that our solution y of t, that's equal to some constant k1 times x of, and it's alpha plus I beta. And we should say beta 1. This is alpha 1. And this is t times all this. So it's t times all this. So that's the first term. And then the second term plus. Right, so that's in our process. This will be the solution eventually, right? And our solution depends on the eigenvalues of the original question, right? So if you go back to, so I'm going to take as the starting point the differential equations. Is everyone happy with that? We had established that the eigenvalues determine the time constant. So the eigenvalues of the original problem. So there does exist an original problem dy dt equals ay. And so we said that whatever our process is, we could eventually pose it as a system of first order equations, right? So y is a vector of functions and A is a matrix of constants. So the eigenvalues of A determine the time constants here. So this is one eigenvalue. Here's another eigenvalue, right? Is everyone happy to take that as the starting point? Okay. So if that's our starting point, then we are concerned about these alpha values. If even one of these alpha values is a positive number, then we've got e times e to the t times a constant positive. And that means that will go off to infinity. We know this I beta part, x of I beta, that's going to contribute a sine and a cosine. So that part we're not too worried about. We know that there are oscillations in the real world, so we've accepted that. But this part we can't accept. We can't accept if that any of our alphas are positive. If even one alpha is positive, then e to the t times that constant will go off to infinity. So we can't control a process like that. So we are very concerned about that fact. And then let's see, the next piece is, that if we have any region in space, and if we have zeros and poles, right? So in our transfer function, if there are zeros and poles, then the difference between the zeros and poles, so if we minus p, so in our S plane, right, this is the S plane, then we'll draw just now the G plane. So in our S plane, we also showed that that our poles and zeros of the function, so if we have the G function, G equals, and we've got something similar up here, right? Zeros and poles, right? So Z's are where G goes to 0, and P's are where G has a pole where it's going to infinity. So we showed that we could have, if G is of this form, then we have M zeros and P poles. And as we pick a contour, so if we pick a contour like this, so any closed contour, then we could observe how the angle of each of these parts change. So if you start on 0 here, so if you are observing this, this 0, for instance, then as you travel around here, as you pick different points on this contour, then this line is rotating around this point. And when you close the contour, in other words, when you travel through here and you get back to this point, then the angle around this point will have increased by 2 pi. And then for the poles, it will have decreased by 2 pi, right? You'll get a plus 2 pi for each of these terms, and you'll get a minus 2 pi for each of these. So we would say the number of encirclements of G, right? When we say we're adding 2 pi for G, we are saying that as we are traveling around here, as we are moving around on this closed contour, that the values of G on the G plane, so if we draw the G plane here, then the values of G are doing something else. So G is rotating a certain number of times here. So we are saying we happen to know that if we just subtract the number of zeros from the number of poles, we can get the number of times G will encircle the origin right here. Sorry, 1 second, let me clear the background noise. Sorry about that. So we are observing how G changes as we travel around this one contour. So even though we just do one orbit of this contour, G will probably be going through many, many changes. So G might be going crazy here, right? If you have a large number of terms in either one of these, then G will go through many, many changes. But we will be able to determine how many encirclements G will make from this expression. Now, if we have, if the process is inherently stable, then we can say that the number of poles let me just check that. Yeah, if it's inherently stable, then your number of poles is greater than your number of zeros. And, or rather, Q is more than M, right? Not your, your number of poles is greater than your number of zeros. That's one fact. And also, if it's inherently stable, then you will not have any poles in the right-hand plane, because the poles here, right, again, if you go back to those differential equations, the poles are the lambdas. So these things in the real world, right, if you look at your Laplace transform, so Laplace transform of e to the at equals 1 over s plus a, right? Using this simple fact, we can see that the eigenvalues a are the same as the poles here, right? You agree a is a pole here, or minus a is a pole, right? So that's a pole. So the time constants show up here in our poles. So we are very worried about any of these poles having a positive real part. In other words, all our poles need to sit in the left-hand plane only. So if this is the S-plane, we want all our poles to sit in here. Now, when we drew this, this contour, we said, yeah, this is an arbitrary contour. And this is true. It's an arbitrary contour, and this relationship holds for any arbitrary contour. Now we are going to pick the specific contour which goes around the right-hand plane. So we'll say what we are really worried about is this entire right-hand plane here. And so we are saying that we need to travel around the entire right-hand plane and observe the number of encirclements by G. So if G encircles the 0 point at least one time, then it means we have one more 0 than the number of poles. We can also say that, well, there shouldn't be any poles at all here, because if we are requiring that the process is inherently stable, right? Inherent stability means that all these poles are sitting on the left-hand side. So we don't have any positive real parts. So if that's true, then we won't have any poles on the right-hand plane. So there are no poles on the right-hand plane. So now we've chosen the contour. So on contour encircling right-hand plane, inherent stability implies that P equals 0. Then that leaves us with that N equals Z. So we know P is 0, but we are worried whether Z could be 0 as well. So if Z is not equal to 0, then that means in the original equation we have a pole. We have a positive real part. So that's what we are looking for. We've established just that P equals 0. Now we want to check whether Z is 0, whether we have a positive real part in the right-hand plane. So to do that, we look at how do we ever travel around the entire right-hand plane. So one part of it is to say go up here, s equals I omega. The next part would be to say go off to infinity and then encircle use a half circle, a half infinite circle, travel around, and then go back on s equals minus I omega. So if we think about this, if we have a magnitude that's going off to infinity here, then if we have a greater number of poles here, then this becomes much greater than the numerator. So when s goes to infinity, if, for example, you've got a cubic down here and you've got a squared only up here, then the cubic will go off to infinity much faster than the square. And so on balance, this will go to 0. In other words, when we travel around here, we are getting a 0. The G value is moving around here. So as S changes around here, G is only sitting here. And then we also know S equals minus I omega is giving us the complex conjugate of S equals plus I omega. So we might as well just travel on S equals I omega. And so as we do that, let's clean up a bit. So as if we are only concerned about S equals I omega, so we are only following S traveling like this, and we are observing G, then if G ever encircles 0 even one time, then that means that there's a 0 in the right-hand plane. So it comes from this, right? So if G ever encircles the origin, then, and sorry, it wasn't, I made a bit of a, there's a piece I missed here, which is G closed loop. G closed loop equals G over 1 plus G, okay? So we need this piece as well. So we said here, G itself doesn't have any poles in the right-hand plane. But then the other thing we are interested in is the poles of the closed loop transfer function. So those poles come from 1 plus G equals 0. So 1 plus G equals 0. So we are interested in this function having a 0 in the right-hand plane. If there is any 0, so we already know there are no poles. We've already said G itself can't have any poles in the right-hand plane. So this part is out. We're left with just this. So we want to know if this function has any zeros in the right-hand plane, because if it does, then that's going to contribute a pole to the right-hand plane of the closed loop function. So our closed loop function will go, our closed loop function, if it has a 0 in the right-hand, if it has a pole in the right-hand plane, that will show up as a 0 of this function. So we are worried about zeros of this function being in the right-hand plane. And so we are worried about encircling that this function will encircle 0, 0. And this function encircling 0, 0 is the same as G itself encircling -1, 0. Right, because of the +1 over here. So instead of worrying about this equals 0, you worry about G encircling -1, 0. Okay, so that's just kind of revising the logic for this. I think I wasn't so organized because I was trying to do it on the fly, but I don't think it worked out too well. I think, let me break this down. So I'll produce another set of notes. And I know we've covered this before, but I'm going to produce another set of notes where all the pieces are in the right order. And yeah, we can establish this again. Okay. Let's see. Okay, so we'll do that next time. So I don't know if that helps, Annika. Yeah. But I will, yeah, as I say, we'll do this again, right? There are quite a few pieces to stick together. Okay, then for now, continuing with this, maybe let's not introduce any other elements. So just do as a tutorial. Yeah, so a comment, it did, but the notes would be nice too. The notes are there. Let me just check your Dropbox folder, should have it. Yeah, it's here. So frequency domain dynamics 07, the same set of notes we're looking at now. So yeah, in this first part, we introduced the basic theorem and all that. And then for whatever reason, I put in all this Bode diagram stuff here. So just jump past all this and go to here, Nyquist stability criterion. Yeah, maybe I should have just pointed here, but yeah, all the stuff we just talked about is here. So your your principle of the argument theorem is here, the justification for that, encirclement, that's all here. But I guess it's not signposted as here's everything is based on these 2 pages. Yeah, so it is here as well. Okay. Right, so do all those problems, try all these out, see that you've got enough experience drawing a Bode diagram quickly, and then use the simulator to check your answers. Okay, any questions or comments there? So if not, then that's it for today. See you next time.